title of talk, Recovering Bicomplex Holomorphic Functions. Please start, Lina.
Oh, thank you. Thank you, Sergey. I am very glad to be here. I would like to thank the organizers for this kindly invitation. Okay, the title of my talk is Recovering Bicomplex Holomorphic Functions. The plan is the following. I will give some preliminaries after a proof of a formal identity, general case, some words about bicomplex holomorphic functions, and maybe some words also about our line integrals, and finally recovering bicomplex holomorphic functions. Okay, well, in this article, Shaw writes a proof of a classical statement of Ahlfors concerning with the reconstruction of some holomorphic function from its real or imaginary part without the use of Cauchy Riemann equations. We recalled precisely that if U is a function defined in some domain U that satisfies the complex type Laplace equation, then we say that this function is harmonic. And in this talk, we give another proof of the statement of Ahlfors, and we show that the bicomplex holomorphic that the bicomplex holomorphic theory is well suited for complex harmonic functions. Moreover, we recover the complex conjugate harmonic function of U, such that U plus iota B is a bicomplex holomorphic function. Okay, first we recalled that if we consider some harmonic function, then it is well known that we can recover from the real or the imaginary part of some analytic function, we can recover the analytic function. And using precisely the Cauchy Riemann equations. For instance, a typical very simple example is the following. This function is, of course, real harmonic, and we can recover the imaginary part only performing this integral, okay? Then, however, if we consider now this real harmonic function, then first of all, it's not so easy to try to prove but that this function is harmonic. And after, if we want to recover the imaginary part, it's necessary to perform this integral. And as you can see, it's not so easy to try to solve this integral. Okay, well, okay, now we recall that in his classical book, Complex Analysis, Ahlfors wrote this sentence, these arguments. Okay, if we consider some analytic function f, whose real part is given by u, then the conjugate function f bar has a derivative 0 with respect to c. And then we can consider this function as a function of c bar. And we denote this function by f tilde of c bar. With this notation, we can write this identity. Okay, you can be the real part can write in this form, and then he wrote that it's reasonable to expect that this is a formal identity, and then we can substitute x equal c over 2, y c over 2e, and we obtain precisely this relation. And using this relation, then we can recover the analytic part, the analytic function f, using only the real part. Okay. Well, this is exactly the text of Ahlfors. However, of course, this is a formal identity because x and y are real numbers. They are not imaginary numbers, complex numbers. Okay. They are not complex numbers. Well, we try to give in this moment to give some proof of this formal identity in the following form. Okay, for this reason, we consider some double series of complex numbers. And we recall that this series is convergent if, of course, is absolutely convergent. If this supremum is finite. Okay, where lambda supremum of these partial sums is finite. Okay. Well, now we consider this double power series. Okay, and this is of course we consider this polydisk, and then we consider that these power series converge in this polydisk, in this complex polydisk. Of course, this series represents some holomorphic function in two complex variables, C1 and C2. Okay. Then now, if we consider some holomorphic, because all this theory, because we want to recover the an analytic function from this from its real part, we will consider this is a local result, but we will consider the unite disk. Then we consider an holomorphic function defined in the unite disk. Okay, then we expand this function in its power series of Z, okay, with development, and then finally we decompose F in its real part and its imaginary part. Okay, here the coefficients Bmn and Cmn are real numbers. Okay, then we have here, we can write then the real part of F using this power series, real power series, and the imaginary part using this real power series of X and Y. Okay, and now our series about F of F power series converge absolutely in this in this circle. Okay, then we can estimate absolutely this power series. This is finite, and now we consider the real variables X and Y in this square. Here is the circle, and then we consider this squared. This is the we consider then this square, and then each series converge absolutely in this square. Okay. In particular, then we have this estimation. Okay, for each R, for R capital given of this form. And then now, in particular, in this square, we can consider this real analytic power series expansion for the real part. Okay. Now, we now consider the polydisk, the complex polydisk. You see here. Okay, the complex polydisk, and we are using exactly the same definition of the real power series expansion of U. This capital U is a function that depends of two complex variables, C and W. Okay, and of course, because we have this estimation, there is no problem with the convergence of this series. Then this series is holomorphic functions in two complex variables, C and W. Then, of course, we know that U is the real part of F for each C in the unit disk, and of course we can develop the real part using its real power series expansion. And now we will consider points because we want to consider the convergence of the real power series expansions in some disk. Then it's now necessary to consider this disk with radius r over square root of 2. Okay, and then we consider the same. Here there is no problem with the convergence of this real power series expansion, but now we have then in this circle we have the equality, the equality of capital U in XY. Recall, and we are substituting, we are changing here z by x and w by y, and then we have exactly this equality. And moreover, we can consider now these two variables. We substitute in capital U c over 2 and instead of w, c over 2e. Then we get this power series expansion. In particular, this power series represents some holomorphic function in the variable z. And we can define this P of z using this equality. And of course, this is an analytic function in the disk with center 0 and radius r. And if we recall the definition that give Ahlfors f tilde of z, f tilde of z bar is given by this, then we have exactly this equality, but now here is capital U. And then you can observe that here, in fact, we can substitute, instead of x, we can substitute c over 2, and instead of y, c over 2e. Okay, because now there is no problem, because we can put here complex variables here without any problem. And then we close this part using this equality again, and then with this we have the proof. We have the proof, and we can so we have a recover, because we can consider that it's real. We can recover fc using only the real part, okay, by this expression. There is a proof then of this very classical result of Ahlfors. However, there is not in general, there is no proof of this result in the book, in the textbooks of complex analysis. Now we will consider the following general case, okay? We will consider these functions h1, h2 that depends of two complex variables. It is only given by this expression, w1, w2 equal to w1 plus e w2 and h2 using this conjugation given form in this formula 3.9. And then we consider, since that these two functions are continuous, then omega tilde defined of this form is an open set in C2. And because of this definition, it's possible to give a precise definition of omega tilde. It's described in this form: C minus bar C prime over 2, C minus conjugate of C prime over 2it, C and C prime in omega. Moreover, if C is in omega and C prime equals 0 is in omega, then these 2 points belongs to omega tilde. And now we consider any function, from omega to the complex plane. And we will define U tilde from omega tilde to Z by this formula. Okay, this is a function that depends of two complex variables. Okay, two complex variables. And here is the definition, but here we are using a function that depends on only one complex variable. But there is no problem, because we define in precise form omega tilde and with respect to omega. And then we define in this form, okay? And again, we have now this equality. If we change W0 by C over 2, W2 by C over T, then we have this, okay? And again, if we substitute now W1 by X and W2 by Y, then we get again that we recover the real part of F using U tilde, okay? In this sense, U tilde is a natural extension of U. Okay, these formulas are given by Shaw, okay? These formulas are given by Shaw. However, it is necessary to have caution with the following thing. For instance, if we give this function f given f of c equal to x minus the integral part of x. And if we substitute directly the change of variable c over 2e, then if we substitute, the formula does have any sense. Okay? Well, by this reason, it is necessary to prove really, to give a proof when it's really possible to substitute c over 2e in the expansion in the formula of u. Okay. However, if we use precisely the definition really of u tilde, then we get this formula. And of course, we can apply this formula. This is really a right formula, not the previous. Then by this reason, it's not possible to, in general, to substitute directly this change of variables. Okay, and now this this formula from here has the following interesting situation. If we calculate this complex Laplacian, observe that W1 and W2 are complex variables, then this complex Laplacian is zero. So, okay, then we say that G is complex harmonic. This is complex harmonic. Okay, there is some theory donde this definition it is very interesting. For this reason, it is necessary to introduce the bicomplex holomorphic functions. And we consider then the ring of bicomplex numbers BC, and is defined of this form. Is given by C1 plus iota C2. C1 and C2 are classical complex number, and iota is some another imaginary unit different from E. And sum and product of bicomplex numbers are made in the expected way. Okay, and this is some kind of imitation of the classical complex numbers. Okay, however, we can write in different forms bicomplex numbers. Here's using their C idempotent form is given of this form, where the change of variables are given by these two formulas. Are called idempotent because the definition of these two numbers satisfies precisely these idempotent identities. Okay, here there are several conjugations in bicomplex numbers. We consider only this conjugation, see, and it's possible to define some bicomplex holomorphic theory here using precisely the limit of this differential quotient. Okay, of course, it's necessary that C minus C0 is should be an invertible complex number. Okay, two consequences. If the function is the complex derivable, then there exists these two complex partial derivatives, okay? And moreover, this complex partial derivative satisfies this equality. And this equality is equivalent to the system. This system is a Cauchy Riemann equation, but this is a complex Cauchy Riemann equation because C1 and C2 are complex variables, okay? And then from this, we get directly then that F1 and F2 are conjugate complex harmonic functions, okay? Then one function is the complex variable, the complex holomorphic, if and only if satisfy this Cauchy Riemann system. And as a consequence, each component of F is the complex, satisfies some complex Laplace equation. And they are, of course, conjugate complex harmonic functions between them. Okay, now, let me skip this. results. In this theory, very quickly, in this theory, it's possible to consider line integrals and to write all this theory without any problem. And there is some chain rule. For instance, here, if we consider that f from omega to bc is a bicomplex holomorphic function, and gamma is a piecewise C1 curve, then we have this chain rule. Okay, here is a bicomplex multiplication here. However, all is okay with the chain rule, and so we have the following result. Like in the classical complex theory, if we consider f1 a complex harmonic function, f1 a complex harmonic function, and the first homotopy group of omega is trivial, then we can calculate all the conjugate complex harmonic functions of f1 and are given by this formula. Like in the classical complex case, we can recover the conjugate in such form that f1 plus iota f2 is a bicomplex holomorphic function. Okay. How can we recover the other component using only the first component of some bicomplex holomorphic function? We can use this proposition to estimate the norm in R quad, in R4 of Wn is given in this form. There is no equality. There is no equality because here we have a multiplication of bicomplex numbers. In general, for bicomplex numbers, the estimation of the R4 norm is given in this form. Then we have this, but then we can recover then if we consider some bicomplex holomorphic function defined in some set of the bicomplex numbers in some domain, and these are the two components of f, then we can recover the bicomplex holomorphic function using only the first component or the second component. And the proof is very similar to the classical because then f1 in particular, f1 can be writing the first component can be writing as a holomorphic function in the variables c1 and c2. And then again we can estimate in some polydisk we have some estimate, and now we consider this bicomplex polydisk. To avoid problems about convergence, we consider here the radius R02. Okay, here these power series converge in this polydisk. Now we consider this bicomplex polydisk, and now we will consider precisely, you can see here, now we will consider f1 tilde, but now this function depends of two bicomplex variables and is given again in similar form that in the previous one in the classical. Okay, then we define in this form this f1 tilde. Of course, there is no problem with the convergence of this series and the bicomplex. There is not a problem because we have these estimations. Of course, also of course we can write the component f1 in terms of this. This is the conjugate, one of the conjugates that we are using in the bicomplex case. And again, now we see that there is coincidence when we evaluate f1 tilde in c1, c2 in these complex numbers, okay, and this equal to f1 in c1 plus iota c2. And now, again, if we consider now the bicomplex variables c1, c2, and we choose w1, the bicomplex variable c2 comma, C over 2 iota, C capital is given here, then again, we get this formula. And here, we get precisely the power series expansion of F1, of F1 here. Here is C1 and C2, okay? There is some small mistake there, okay? And finally, then, we have exactly the statement of the theorem. F tilde of C1, C2 in J can be recovered in this form. Can be recovered in this form without any problem. Then the situation was exactly the same that in classical case, but now it was necessary to change, to consider our function in two bicomplex variables, And finally, only to end, we consider now f a bicomplex holomorphic function in a neighborhood of omega, and a point in omega, then we can recover again f from the real from its first component or second component locally at a point A if we use now this change of variables. Here is f1 tilde, f2 tilde, but it's possible to consider the formula using only at a point different from 0, only using these transformations. Okay, well, okay. Here's a sketch of the proof, but only to finish, I will present this complex harmonic function is given by this formula, and then we apply directly our formula. We know that it's possible really to substitute instead of C1, C capital over 2, C capital over 2 iota. We substitute and we get exactly, which is the formula of the bicomplex function, FC. Okay, so thanks for all. Thank you very much.
Okay, let's thank Professor Lino Resendis for his very interesting talk. Some comments or some questions? Thank you.